Hello, and thanks for joining me at the 31st International Ocean and Polar Engineering Conference, where I will be discussing the influence of leading-edge tubercles on the hydrodynamic performance and propeller wakeflow development of a ducted propeller, a research study conducted by myself and Dr. Wei-Chao Shi at the Naval Architecture, Ocean and Marine Engineering Department. Firstly, I will give a brief introduction where I will discuss the importance of improving propulsor hydrodynamic performance and the previous research about leading-edge tubercles. Then I will outline the hypothesis drawn from the previous research and the aims and objectives of the research study. Then I will describe the test case geometry, the numerical methodology implemented, and the verification and validation procedure. Finally, I will discuss the most significant results and draw some conclusions from the current study. Then I will discuss our planned future work. Improving hydrodynamic performance of marine propulsors is an ever-present aim due to economic pressures and regulatory requirements, where it can also reduce ship fuel consumption and thus save the ship owners money, but also reduce carbon emissions, a key challenge within the maritime field and the world. Most energy-saving devices focus on open propellers, and therefore the potential improvement in ducted propellers performance is sometimes left behind. To improve the hydrodynamic performance of ducted propellers, we can look to nature to try and solve our problems. Leading-edge tubercles are inspired by the small bumps on the pectoral fin of humpback whales, where they improve the whale's ability to perform acrobatic maneuvers to catch prey. They have been researched on applications such as airfoils, hydrofoils, and tidal turbines, and they've shown to provide benefits such as delay of stall, improved lift-to-drag ratio, a reduction in cavitation severity, and subsequent underwater radiated noise reductions. These benefits are believed to be due to the counter-rotating vortex pairs that can be seen in Figure 4, and these are induced by the leading-edge tubercles. Duct performance is highly related to the lift and drag force vectors as shown in the figure below, where the thrust produced by the duct is the net horizontal component of lift minus the drag component of the duct. Therefore, from the previous literature, we can form a hypothesis where if the tubercles were applied to the duct of the ducted propeller, they would improve the hydrodynamic performance of the duct, particularly in off-design conditions where flow separation could be incurred, such as at the high advance ratios. However, at this point it would be unknown what the influence tubercles would have on the propeller performance due to induced streamwise vortex pairs from the leading edge tubercles into the propeller inflow. In addition to this, it would be unknown whether or not the vortex development in the propeller slipstream would be affected by the introduction of additional vortex structures in between the propeller and the duct. So this brings me to the main aim of this research study, which was to investigate the influence of tubercles on the hydrodynamic performance and wake development of a ducted propulsor. And this could be achieved by completing three objectives, which was firstly to design a tubercle ducted propeller and select a reference geometry, secondly to quantify the change in hydrodynamic performance, and lastly to understand the underlying flow mechanisms behind the change in the hydrodynamic performance and the wake flow development. So the reference geometry selected was the accelerating 19A duct along with a 4-bladed Kaplan propeller with a 0.55 expanded area ratio. This ducted propeller combination was selected as it's very popular and is used among vessels such as fishing boats and tugboats due to its enhanced maximum thrust capability in heavy loaded conditions. Then the tubercles were applied to the 19A duct as can be seen in figure 6 and denoted SLE for sinusoidal leading edge. The tubercle geometries, wavelength and amplitude, which can be seen in the tubercle schematic in figure 7, were based on previous optimization research, and a variety of different operating conditions were considered within the current research. Commercial CFD code STAR-CCM was used to perform the analysis, where detached eddy simulations were used. This solves the near wall regions using a RANS-based approach, and the rest of the domain using large eddy simulations. The RANS turbulence model used was the SSTK omega turbulence model, and a sliding mesh technique was used to define the propeller rotation. An unstructured hexahedral mesh was used, and this cell count was around 13 million cells, and the whole boundary layer was resolved using a fine prism layer mesh with the Y plus value being below 1. A grid convergency study was used to determine the uncertainty error within the simulations. Key variables total thrust and torque were used to determine the error within the simulations using 3 different mesh structures, and the uncertainty error between the medium and fine grids was below 1% for both variables, and therefore the fine mesh of 13 million cells was selected for all future cases. Next, the open water hydrodynamic characteristics obtained in the CFD analysis were compared to the experimental data, and as can be seen, there is a good agreement between thrust, torque, and efficiency for the numerical model, and therefore the CFD was validated. So looking at the global hydrodynamic performance change due to the inclusion of tubercles onto the duct of the ducted propeller. Firstly, we can see from J equals 0.001 to J equals 0.4, there's an improvement in duct thrust, and this is due to the inclusion of the tubercle peak and the surface area, which will introduce an extra lifting surface and thus enhance the thrust performance of the duct in the heavy loaded conditions. Then at J equals 0.5 we can see there's a reduction in duct thrust, and this is due to the early inception of flow separation on the pressure side of the duct. Then we can see at J equals 0.55 there's an improvement of the duct thrust of around 7 to 8%, and this is due to the control of the flow separation, which can be seen in this figure here, where the tubercle compartmentalize the flow separation and focus the flow separation to the troughs of the tubercles, and therefore this enhances the thrust performance of the duct. And at J equals 0.6 we can see there's a decrease in duct thrust performance, and this is due to the tubercles in this particular configuration not being able to manipulate or control the flow separation behaviour happening on the pressure side of the duct, and therefore the additional surface area likely creates extra drag, which will reduce the thrust performance of the duct. Another interesting point is the reduction in the propeller thrust and torque at every condition here. And why this is happening is when the tubercles are introduced into the duct, they induce these streamwise vortex pairs, and these interact with the propeller and result in the reduction in the propeller thrust and torque. And these can be seen here in a plane section of the streamwise vorticity, where you can see around here that there's no streamwise vortex pairs present, whereas if you see the sinusoidal leading edge propeller inflow, you can see the current rotating streamwise vortex pairs that are being introduced into the propeller inflow. So then, looking further into the propeller wake flow development, what we can see in this figure is the turbulent kinetic energy plotted at different positions with respect to the chord length of the duct downstream of the duct propeller, where 0 denotes the propeller center. Now what we can see here is the y-axis, the positive y-axis denotes a turbulent kinetic energy reduction when comparing the sinusoidal leading edge tubercle duct to the reference duct. So what we can see here is initially the turbulent kinetic energy of the sinusoidal leading edge in the wake flow is a lot higher than in the reference duct. But as you move further downstream, you can see that the dissipation in the turbulent kinetic energy is much improved by the sinusoidal leading edge, and this can be shown by the reduction in the turbulent kinetic energy at all operating conditions considered furthest downstream of the ducted propeller. So looking further into the vortex development in the ducted propeller slipstream, firstly we can identify the different vortex mechanisms. So initially we can see this initial tip leakage vortex being created. We can also see the blade trailing edge vortex, and lastly we can also see the hub vortex and the secondary vortex mechanisms that are being rolled up into into the initial tip leakage vortex. Now, the vortex breakdown in a ducted propeller slipstream is believed to be primarily due to the shortwave instability in the initial tip leakage vortex and the secondary vortex mechanisms that cause the breakdown in the vortex structures. And what we can see here is that the initial shortwave instability in the tip leakage vortex is a lot more pronounced for the sinusoidal leading edge case. We can see it's a lot wavier, which shows an increased instability or increased shortwave instability, and this is believed to be due to the additional streamwise vortex pairs that are being introduced into the propeller inflow. And what this does is this can accelerate the vortex breakdown in the propeller slipstream. So if I take, for example, this section here and this section here, we can see that there's a lot more breakdown in the sinusoidal leading edge slipstream at this section here than compared to the reference. So it can be said that the vortex breakdown happens earlier in the sinusoidal leading edge than the reference duct, which accelerates the dissipation in the vortex structures and the dissipation in the turbulent kinetic energy. So to conclude, the inclusion of leading edge tubercles onto the duct of the ducted propulsor can improve the duct thrust performance by a maximum of 7% due to the flow compartmentalization, and this is seen at the higher advanced ratios and on the pressure side of the duct. In addition to this, at high blade loading conditions, tubercles can create additional instabilities within the initial tip leakage vortex, which can accelerate the vortex breakdown and turbulent kinetic energy dissipation in the duct propeller slipstream. And this fundamental understanding leads us to believe that there could be a potential reduction in underwater radiated noise due to the reduction in the strength of the turbulent wake structure in the duct propeller slipstream due to the inclusion of tubercles, and this is something that is a planned future work for the authors. So if you're interested in the research presented here today and want to ask any questions or have any discussions, please feel free to contact me on my email, and if you're interested in any future work that I will be conducting, then please connect with me on LinkedIn as well. And if you're interested in other biometric related research in the marine industry, please check out our research group website, ABM Hydro, and thank you very much for listening.